when you're up against that, there are ways around it, but it does significantly raise the bar for getting up and running. But when it's done right, it is one of the most common file types that we execute. All right. Yeah. So thanks for coming to my talk. This is Modern Malware. So we'll go ahead and kick off. We'll talk about the who and the why of where this talk came from. So initially, as with most of my talks, I try to make something where these are the things I wish I had had when I was coming up. These are the things I wish I could have referenced as I was learning to become a pen tester, red teamer, that kind of thing. So I initially started out with this for red teamers, for pen testers, for the internal security teams that are testing these things. But I also started hearing from some of our clients, some of the blue teamers. They were saying, all right, it's awesome. You guys come in here year after year after year, and you always find some way to kind of wiggle past the endpoint protections and that stuff that we have set up. What can we be doing in the off season, before you guys come back again next year? What can we be looking at? What can we be testing? So I wanted to kind of lay out, just high level, some of the topics and some of the considerations that we have to go through when we're writing our shellcode loaders and our malware that we're going to be using on a test. And then as far as the why goes, Jeff McJunkin, awesome dude. He's on a lot of our Wednesday offensives. He said, everything's stealthy until they're watching for it. So and there's a lot of truth to that. The easy stuff that you hear about in the news could be something that 98% of the companies out there are blocking. But if your company's not blocking it, and one of the malicious actors happens to use that technique, well, that's something that you need to make sure you're prepared for before they get there. So kind of wanted to touch on this too. So the security is a cat and mouse game. I can't tell you how many times, we're on a 2-week test. Friday afternoon, we've got code execution. We're up and running. We're like, oh my God, next week is going to be awesome. We're actually going to get going. Come in on Monday, and of course, the security product, the security team, they kicked it into overdrive, figured out what was going on, and they started blocking it, which is awesome for them, not so awesome for us. So make sure you have, if you can, you have some kind of contingency plan for if those things start getting blocked. Another thing is keep it simple. There have been more than a few times where I'm just throwing the kitchen sink at it. I'm throwing in multi-layered shellcode loaders, as much evasion as I can think of, only to finally turn around and throw a PowerShell script loader at it, and it just sails right past everything they have. So make sure you try to keep it simple. Don't discount the easy stuff, because the easy stuff could be what gets you up and going. Another thing, every environment's different. We test a lot of Carbon Black, CrowdStrike, SentinelOne customers. I could be on a test against one of these products one week. I'm just sailing through like nothing's really slowing me down. Everything's going great. And I'm like, start getting a little full of myself, a little cocky, and then go to the next week and I just absolutely get destroyed. Like I cannot do anything but without them just completely shutting me down. So, just because it worked in one area doesn't necessarily mean it's going to work in another, but you kind of start picking up on patterns as you go. And then finally, nothing here is new or groundbreaking, but it could be new to you and your team. So a lot of these things are things that I've just picked up along the way, things that I've found, in the 11th hour when I was trying to get up and going. And that's, we want to make sure that the basics are out there so that you understand what all goes into this. Now, I wanted to throw this in. I like to say this just first and foremost, all the props go to the researchers, the open source tool writers. Those are the real kings sitting up there in their thrones. That's just me at the bottom running around acting like I know what I'm doing. So, all right, So let's jump in. So quick rundown of what we're going to run through. We're going to talk through some of the initial considerations that go into what we think about when we're getting ready to write a malware loader. We'll talk about some of the initial protections and detections. These are just the very basic things that you're going to find in like a Windows environment. Next, we'll talk about the sandbox and how you can kind of evade that to make sure that the security products think you're doing something legitimate when you know you're not. Then we'll talk about some static detections, which this is when our malware has to live on disk or it has to stay there for an extended period of time. We want to be able to sit on disk without any kind of file scanners or that kind of thing coming along and just completely removing our malware. Next, we'll talk about some of the common execution methods that we use. Again, these are not going to be anything too crazy, but it is stuff that we use very, very commonly on our tests. And then finally, there's a slide full of some resources for those who want to kind of go through and study some of these subjects. So let's start talking about the initial considerations. First and foremost, obviously, most of your malware is going to be written in C, C++, right? But you can get a lot of the same mileage out of .NET frameworks. This would be things like PowerShell, C#, and we've started using some of the F# as well. You saw Justin Paulk earlier. He's been working on some F# stuff, along with Trunzer and his team that used to be contributing stuff with F#. But those .NET languages, especially in a Windows environment, can really take you a long ways. And then also the VBA. So this one we're not using as much nowadays, just because the Office docs they're not dead, but they're more of a kind of second wave of malware versus your initial infection vector. But those are the languages we're using the most often. Occasionally, we are using Rust, Golang, Nim, Python. Pretty much, it's whatever the client environment requires. But the languages on the right are the things that we're using basically when we have to. The ones on the left are the things that we're using the most commonly. Another thing I wanted to include was a kind of a slide full of different file formats that we take advantage of. Of course, you've got your .exes, your portable executables, and your dynamic link libraries. Those are probably the two most common, but those are also heavily scrutinized. So another one that we use pretty commonly are XML files. These are files that contain things like C# or F# code that we use in conjunction with other tools to get our payloads up and running. Another one we use pretty commonly are MSI files, the Microsoft installer files. The great thing about these is not only can you execute commands with an MSI file either before or after your supposed installation, but you can also use it as just a file dropper. This can actually drop files to disk depending on where you tell it to, and that can be a way of smuggling files into a target environment. Another one are the Word and Excel add-in files, the WLL and XLL. Again, these kind of fall under the same constraints as macro docs. So if it came from the internet, it's automatically blocked by default. But as a method of persistence or as a method of execution after the fact, these are still things we use pretty commonly. It's just not necessarily our initial infection vector. HTAs, we use those every now and then. We don't use them as much nowadays, but they are still pretty viable. Click once applications are basically just published .NET apps. And then, of course, the old batch and command files, those get used pretty regularly as well. And with the Microsoft JScript, when you would do the attacks like the Squibbly do, that's stuff that you can still get away with, but it's a little more monitored nowadays. So another big thing that we run across, I've been told by other pen testers that they're like, man, I'm sitting here on my box. I've made the malware. I've got it up and running. As soon as I download it through a web browser to my target host, like on an assumed breach type deal, it's getting stopped almost immediately by the Windows Defender Smart Screen or something like that. So the things that you work on in your lab, it may be working perfectly, but as soon as you download it from the web, it's looked at in a completely different context. So to simulate delivery, like what your target would be experiencing, it's good to try and download it through a couple different means. I would recommend downloading it just straight through a web browser. Download it through PowerShell through either a download cradle or some other method. You can use Bits Admin, which is a built-in Windows function for transferring files. Or if you've got Windows 10, I don't know, 2021 or above, I believe, you actually have curl.exe built in, which is exactly like the Linux binary. So all of these methods are ways to pull the file down from, like, say, a web server or some kind of web dev, that type deal. The thing you got to look out for, though, when you download these things, and this is why it may be treated differently if it comes from the web, is a zone identifier gets attached to files that are downloaded. These, and you might hear this commonly referred to as mark of the web, or MOTW. And what this zone identifier is, it's an alternate data stream that gets attached to the file. So it's not something that shows up immediately, like if you look at the properties of the file, but there are ways to view what that alternate data stream is. So in the NTFS file system, this is something that gets attached in a way that's not immediately obvious until you look with something like the PowerShell command here shown at the bottom. And I'll actually show you an example of this here in a couple slides. But that mark of the web is, as I said earlier, is kind of how Windows Defender can tell that this came from the internet versus something that was sitting on disk already. So some bypasses that we commonly use to get around this are, you can create a dropper file. I talked about that earlier with the MSI file. You could drop an encoded or an encrypted file and then use the MSI to actually decrypt that on disk. You can base64 encode the file if it's embedded in something like to do an HTML smuggling attack or something like that. The only problem with that is, typically, unless the code itself is also is creating a new object or a new file, then the zone identifier can actually get passed on to that. So you have to make sure that you check these things before you send it into the client environment if that's what you're trying to bypass. Another form of bypass are container files. This would be things like archive files, like zip files, which Microsoft has really started paying attention to that. But there are still zip utilities, third-party ones out there, that do not attach mark of the web when your payload file is extracted. Another one, and this is another Linux binary that's been turned into a Windows utility, is the tar. Tar archives. You can, if you use the Windows tar utility and extract a file downloaded from the internet, it actually does not attach mark of the web. And Microsoft is aware of the issue, but they have not patched that yet. So that's probably something that's coming, but for now, it still works. Another one is virtual hard disk files. This would be like VMDKs, VHDs, WIMs. The only problem with this is you have to have admin access to mount these files in a lot of cases, unless there's some kind of specific configuration allowing that. So you would have to be targeting a user that you're fairly confident has elevated access on their box. And then used to, the old standby was using like an ISO file. So if you just packed it into an ISO, even low privilege users could mount those by just double clicking the file, or the ISO file. But Microsoft got wise to that, and they've started attaching mark of the web to anything that comes from an ISO now. So I wanted to show this here. What I did was I just basically renamed cmd.exe to test.exe, and I threw it up on a web browser and downloaded it from from the droplet that I had spun up Apache on. And when I downloaded this through Firefox, as you can see, this is the zone identifier. This is how Windows knows that you pulled this from the internet versus having it on disk already. And this is only visible if you look at it through here or if you reference the zone identifier specifically through cmd.exe. Now, if you'll notice, I took the exact same file, put it inside of a tar archive, put it back on the same droplet, downloaded it, and then extracted it. And if you, as you'll notice here, there's no zone identifier after extracting it using the tar utility built into Windows. So now that we've kind of talked about some of the initial considerations, let's talk about some of the initial protections and detections that you'll run into on a Windows host. The first and foremost is the anti-malware scanning interface, or AMSI. This is how Defender performs antivirus actions. Basically, it's set up exactly like a normal antivirus, where this is signature based. So these are the things that they have determined are definite signatures for just off the shelf malware. So just like a normal antivirus, there are ways around this, especially by just breaking those signatures. But the interesting thing, at least from our perspective, is that this is loaded in userland. And because it's loaded in userland, the user has full access to modify the AMSI .dll that gets loaded into every process. Now, again, this can be bypassed, but bypasses are also being signatured. So you get into the cat and mouse game of trying to get around those signatures to get rid of the signatures that were blocking you in the first place. So some of the bypasses that are out there, of course, you can just modify the signatured strings. There's tools like Threat Check and Defender Check where you can run your payload through that, and it'll tell you exactly what Defender was flagging on. Now, it's not 100% accurate. Sometimes Defender returns some kind of wonky results, but for the most part, it's going to show you exactly what the offending bytes are. So in that case, you can just go in, you can say, okay, cool, it's flagging on this particular word or this particular function. I'll see what I can do to obfuscate that so I can get around it. Another thing you can do, so AMSI has a scan buffer. It's basically a section of memory where it reads the file in, and that's where it starts kind of cutting it up to figure out, does this match any of the signatures that we've got? But what you can do is you can actually patch the AMSI.dll, that you can patch that particular function to say that the buffer is actually 0 bytes in size. So because it can't scan anything, it just automatically passes. And from that point on in that process, it'll just allow whatever is going on, at least as far as AMSI is concerned. Another one is the AMSI init failed function. You can actually just patch that so that it returns the AMSI never initialized. And because of that, now everything's up and running. So another thing is you can find older versions of tools or command interpreters that didn't actually have AMSI integrated into it. One of the most common is PowerShell version 2. So if you launch PowerShell with the hyphen version 2 flag, you'll actually be running in the older version of PowerShell. Now this is it's required that you have .NET version 2 installed, which is a feature in Windows. So, but as the Windows continues to evolve, like the Windows 10 and 11 versions, they've started making that optional and not on by default. So that is something that your target environment would have to have enabled ahead of time. And then finally, you can go to AMSI.fail. That's actually a website where you can get randomized AMSI bypasses. And basically, these are obfuscated. But they do a lot of the same things. However, because the language is constantly being modified and the variable names and that kind of thing, it actually gets around a lot of the signatures. So, in response to attackers taking advantage of AMSI and kind of some of the more fragile detections there, Microsoft developed something called ETW, or Event Tracing for Windows. This is more of the behavioral detection. They look for certain certain orders of operation of things that are pretty much known to be malicious or known to be out of place. A lot of EDR products, they have custom consumers for this. On top of that, Microsoft also has the ETWTI, which is the ETW threat intelligence, where that's what you're seeing when you see the cloud detections and that kind of thing. And basically, what this is going to be doing is it's going to be watching for certain things, and the EDR products that use this as well will create custom consumers that are watching for other actions that may not be monitored by default. Now, all of the API calls for this are contained in ntdll.dll. So if you tamper with that, that can be detected. But at the same time, if you do successfully change those API calls so that they're not working anymore, you can actually get around a lot of detections and kind of blind either the EDR or the Defender product as you're using it. So some of the bypasses, of course, this would also be in the same vein of just obfuscating known strings. While this is not necessarily exactly like AMSI, where AMSI's looking for specific things. ETW may be looking for those things in conjunction with other things. Like you launched an executable and it contains the string Mimikatz or Rubius or something like that. That could be enough to just set it off right off the bat. Even if it were something that we're saying it wasn't going to be running these tools, just having that string in there could be enough to tip it off. Another one is, especially in .NET, is changing the signatured namespaces. Just by doing that, sometimes that's enough in and of itself to get around any kind of detections. And then in tooling that especially that you download from GitHub, they're going to have a default product title, a default product name, a default GUID, those kinds of things. Just going in and changing those default values to literally anything else can be enough to get around it. And then, like I said earlier, you can patch the API call hooks, which are, a lot of your EDR products are making sure that any actions against these APIs are being monitored, and we'll kind of go into that a little bit more here in just a minute. But what by patching that, again, you can kind of make ETW stop watching what it is you're doing, and you can stop the collection of behavioral data on your beacon and continue to run well beyond when you should have been caught. So I kind of mentioned this a little bit in the last slide, but so the hooks are basically ways to divert code execution to the DLLs that your EDR product has running in memory. So an example of a hook would be right here in this NT read virtual memory, where you would see the API call immediately starts with a jump to another section of process memory. So most of the time, what this means is that API call is jumping over to somewhere else where they can start recording the behavior of what's happening when that API call is being called. Now, for a legitimate one, you'll notice that the assembly here is actually just setting up the stack with whatever arguments were passed to this API call so that it could perform the actions that are contained within NTDLL. But because this one up here is actually hooked, you're actually going through a whole other set of detections and a whole other set of monitoring from the security products. So a lot of times when we need to remove these hooks, basically what we're doing is we're either going through and restoring the original arguments to these API calls, and just basically searching for these jump calls to see which ones are leaving NTDLL. So when we go through here, there's a few different ways to clean this up. We can either go through each one and overwrite it with the stock bytes, set it back up so that the assembly is passing in the arguments. We can actually just go scorched earth and overwrite the entire DLL and process memory with a clean copy from disk. One of the cool methods that I saw, a guy named Matt Eidelberg over at Black Hills wrote a tool called Freeze. And this is kind of a malware loader, malware obfuscator. But what it does is it will actually grab a sacrificial process and it'll start that in a suspended state before EDR has had time to patch any of the DLLs in memory. And then it'll actually copy that DLL from the process space of the suspended process into your malware loader's process so that it overwrites all those without actually having to pull it from disk. Because as time has went on and the cat and mouse game has gone on, just reading a DLL from disk and overwriting those bytes can be enough to get you caught. So it kind of turns into a chicken and the egg problem, which came first at this point. You have to figure out a way to overwrite those bytes without being detected that you're overwriting the bytes to prevent the detection. So another way to avoid this is to just not use some of the hooked API calls to begin with. So in Windows, you have to have a way to perform some elevated actions without actually giving the end user those elevated privileges. So the solution that Microsoft came up with was giving you kernel level API call access through proxy API calls. What these are is they usually start with NT or ZW. And what they're doing is if you are allowed to execute or call on this API call as your low privilege user, you're basically just setting up the stack exactly like you would for a normal API call. But then you're using this syscall to actually call the kernel level API call. And that way you can kind of, at least from a Windows level, it can be monitored, and it can also be mitigated to keep from just unnecessary privilege escalation. But what we can do is we can actually just pass in those same assembly arguments, set up the stack, and then actually make the syscall ourselves. So now the only problem is these syscalls do change from Windows version to Windows version, but for the most part, they can actually be dynamically resolved, and we'll have some resources here at the end that can kind of talk through that a little bit as well. But this can be stealthier than the user land API calls because most of these, at least at the time of writing, were not hooked. So again, this is more of an intro to this, so you'll see where these things do get stopped from time to time, but these are things that can be used to get around those EDR hooks. So there's a few different ways to generate syscalls. The most common is syswhispers. I put 2 and 3 on there. 2 and 3 are mostly the same when it comes to 64-bit, but 3 also integrated the ability to do 32-bit syscalls. So if that's something you need, definitely go with 3. But syswhispers 2 is usually good enough to get up and running with a syscall. Another method for resolving the syscall numbers that you need to reference the direct call are put out by the Sector 7 group. They've got the Hell's Gate and the Halo's Gate, which are 2 different ways to kind of indirectly resolve those syscalls so that you can basically make calls directly to the kernel level API call. And then you can also set it up in C#. Using unmanaged assembly code in C#, it's a bit of a daunting task, and it takes a lot of work to get it up and running. But once you get the hang of it, it's not too bad. But it's definitely something that would also kind of stick out like a sore thumb. So it's worth playing around with against your security products just to make sure they are catching it. So now that we've kind of talked about some of the initial detections and protections that we've got to get around, let's talk about the sandbox. So the sandbox is it's like a small virtual machine that's either ran locally or remotely by the EDR or the endpoint protection vendors, and it's a basically kind of a walled off section for in memory for these files to be executed. And what EDR is doing is it's going to execute your malware in a sandbox to see if there's any suspicious behaviors. And it's going to be looking to see, are there any things that we can tell as soon as it executes that we know this is not something that should be executing on our target's endpoint. But at the same time, we can also programmatically tell whether we're in a sandbox when we execute through certain detections, which we'll kind of go through in this section. And if what we can do is we can set our code up to do either something inert or just completely nope out instead of executing our payload and revealing what was actually within our loader. So, one of the first and most common ways of getting around your endpoint protection is to use time. The name of the game is really just slow down execution. EDR products cannot hinder the end user's experience. If they do that, then the end user will complain. They'll switch vendors. Nobody will use a product that actually reduces productivity. So if you can slow your payload execution down long enough, EDR won't stick around long enough. It'll just assume everything's okay because nothing bad happened within the certain time of window of time. So one of the easiest ways to do this is to use Windows API calls for the sleep. You can sleep a certain amount of time and then actually execute your payload. The only problem is EDR vendors figured this out. So what they'll do is they'll actually just fast forward the simulated time if they detect one of these sleep calls, and they'll just basically skip over your sleep period and then immediately execute your payload. Um, so what we like to do is kind of do the delays in kind of a roundabout way. One pretty common one is just to calculate large prime numbers. You can also literally just increment a throwaway variable to like a billion. Like it actually doesn't matter. It's just things to kind of make it look like it's doing something that is pretty innocuous and should be allowed to run. Another one is you can calculate the Fibonacci sequence. The only thing about this one is it is very exponential. You might calculate it out to a certain value, and that takes maybe a minute or two to get up and running. But then you calculate it one more place, and now it takes almost 90 minutes for it to calculate. So you want to make sure that you get kind of the timing down right for that, so that you can get around EDR without having to sit there and wait for 2 hours for your stuff to finally show up. Um, but again, like I said earlier, because the security product can't get in the way of people actually doing their work, they have to kind of abide by this rule for the most part. Another one is to look at the size of the file. So the name of the game is just be too big to fit within the sandbox. There's a couple different ways to accomplish this. You can either pad out the file once it's generated with either zeros or junk data. So guy on our team, Mike Saunders, came up with the tool DigDug. If you're familiar with the old arcade game, basically this will use things like English words or things that are pretty low entropy to expand out the file and make it so that it just doesn't fit in the sandbox. Now, the only problem with DigDug is because it's using legitimate data, when you go to compress that, it's not going to compress very well. Another cool tool that we like to use is a tool, again, by Matt Eidelberg over at Black Hills called Mangle. And what this will do is it'll just pad out a certain area with zeros. So the good thing about this is, let's say your payload is only half a megabyte when you finish it, and you run it through Mangle and want to expand it up to 700 megs. When you zip that down, because the majority of the data is just zeros, it'll actually compress back down to almost the same size as it was before you ran it through this tool. So in that case, you can actually make a believable social engineering attempt to say that my PDF.exe is only half a megabyte, but when they go to open it, it's actually going to expand back up to 700 megs and get around the sandbox. So another one you can look at is the domain status. Is our host joined to a domain? By checking this, you can just check generically to see if it's domain joined, or you can actually check to make sure that the host executing it is actually joined to the domain that you expect it to be joined to. Now, the only problem with calling the domain out by name is you're going to have to know that ahead of time. So you will have to have done some kind of recon ahead of time, either sent in some kind of innocuous payload that gave you that information, or if you're on something like an assumed breach, you can use that to simulate those actions taking place. But a sandbox VM will rarely pass this test. Or at least in my experience, there may be cases where other products have started, making sure that their sandbox reports that it's joined to the same domain. But that is something that we have used pretty commonly to get around those checks. Another one, you can look at all kinds of host attributes for the executing environment. So a normal user's host is going to probably not be using 1024 by 768 monitor resolution. It's probably going to have way more than either half a gig or a gig of RAM. The MAC address, you can tell that right off the bat that whether it's a virtualized host or whether it's, at least reportedly a valid bare metal type host. Looking at the number of processor cores, no one out there is running things on one processor core anymore these days, unless you're running something like a single board computer. The executing username, if you know that ahead of time, you can actually key it to something like that, or even look to see if there's any kind of debuggers attached. But so a lot of these can be broken down basically by either host or by user. So Brandon Arvanagi and Chris Trunzer made an entire repo with a ton of different languages for these checks. You can actually take the code straight from GitHub, plug your stuff inside the loop that checks for these things, and you can kind of get around the sandbox doing that. Another cool thing is you can actually take multiple of these checks and just kind of embed them all within each other, so that it has to pass multiple checks before it ever gets to the point where it'll execute your payload. So now that we've talked about the sandbox, let's talk about some static detections. Now, most of the time we're trying to load some kind of position independent binary shellcode. The shellcode is going to be stored in program variables that can be detected at rest, especially if it's, high entropy or high randomness. Unless you've got some kind of file type that's expected to have high entropy, you can a lot of times this can look very suspicious, when it's got mark of the web. No, your endpoint protection has never seen this file before, and now while it's just sitting there on disk, it either has signatured byte patterns or it's got just large data sections just full of just random data. So unless these are being stored in a way that's expected to be highly random, that can be enough to at least make it suspicious, if not outright be blocked from execution. So the way we can get around that, we can just store the data using known or common data types. One of the more interesting ones is storing it as universal unique identifiers, or UUIDs, because these are 32 byte character or 32 byte fields. You can basically just store your shell code exactly like it would be stored there, because it's all hexadecimal at the end of the day. And then you can just read those UUIDs in and read them back into a memory buffer once it's being executed. Another thing you can do is embed your shell code in a high entropy file, like an image file, like a JPEG, PNG, a GIF. Basically, if you can kind of camouflage it that way and then extract it back out, you've gotten around the detections that are looking for high entropy data like that. Another pretty novel idea from Mike Saunders on our team was to map the bytes to lower entropy data. So Mike wrote a tool called Jargon, and what this will do is you've got 255, 256 possible bytes of data, right? So you map you take a dictionary of English words and you map all 255, 256 bytes to an English word, and then you just store an array of those words and map them back out when it's at execution time. So the great thing about this is it's going to look like that's just standard, data, because it's all normal English words. So it won't look as random, at least to, some kind of scanning type system. And then finally, you could just use a different encryption key every time. So in that case, instead of using the same encryption key for everything, you use, some kind of randomized encryption key, or even using common words. So it's harder to figure out where this is living in memory. A lot of the defense people, when they triage something like this, are going to be looking for some kind of high entropy variable value, because they know that that's probably, at least close to the actual value of the encryption key. So if you can store that using more common words, or using, some of the encoding methods we talked about here, a lot of times that's enough to get around those detections. Another thing is just getting around static signatures. Different compilers optimize code in different but predictable ways. The guys over at White Knight Labs were talking about this, where I could compile the same malware with four different compilers, and it may only be detected by two of the four, or two of the payloads may get detected by your endpoint protection. So definitely try branching out from things like Visual Studio, and try, or using the minimum new compiler for Windows, the Ming W. Just by switching compilers, sometimes that's enough to just fly right past any of the static detections. Another thing is, if it came from GitHub, it's signature. Just because you have access to it doesn't mean everyone else doesn't also have access. So the best thing you can do with projects that you pull from GitHub are just do a find and replace. Just change out certain variables that you know are probably going to be signatured, or things that you see are getting caught by when you're using tools like Defender Check or Threat Check, and just change those out. Sometimes that's enough to just slide right past whatever detections they have. Also, if it's a widely used C2 framework, the default payloads are going to be signatured. We use a lot of Cobalt Strike, Sliver, Covenant, basically whatever the client asks for. A lot of times, if we can't get up and running with one C2 framework, we'll try something else. But we've put a lot of time and effort into going through and trying to change as many of the signatured telltale markers as we can. So another thing you can do, and I kind of touched on this a little bit before, look at the variable names, look at the links. Some of the code will always be setting a buffer of a certain size, and it will always fill it with A's. You could actually just go in the code and change it to where it always fills it with B's, and that sometimes that's enough to just get around whatever detection they're looking for, because they're looking for this specific action to happen. You can change the checksum or the hash of the final payload. One thing that I used to do a lot just to get around detections like that was literally just cat an image file onto the end of an executable. It does nothing to hinder the execution of the file as long as it's only appended to the end, but it will completely change the signature. Now, if you're trying to maintain a signature, that'll actually break it. But if you're trying to make sure that the hash of the file changes so that it's no longer signatured, that's a good way to do it. And then, as I said in the previous slide, change the default encryption keys. Just go through, make sure that your code still runs after you do it. But for the most part, as long as the payload was encoded a certain way or encrypted, those encryption keys are going to work the same to pull it back out. And then again, because we use a lot of Cobalt Strike, we take advantage of the kits that come along with that, which are where you can go in and change certain default actions or certain default behaviors. And you can actually modify the code to do other things before it executes the payload. We use this to do a lot of custom encoding for things that have to get injected into memory and that kind of thing. Also, the Cobalt Strike does come with a script that will go through and randomize a lot of things, randomize a lot of these variables for you. And sometimes recompiling the kits without any code modification whatsoever is enough to get around those detections. So another thing to think about, pretty much your order of operations when you're going to be using some kind of shellcode loader is you're going to provision a memory space or a buffer. You're going to copy your payload into that buffer, whether it's encoded or not. And you can do your decode operations, but for the most part, at the end of the day, you're just copying that into memory. You're going to make it executable, and then you're going to run it. So one thing you can do to get around that kind of static detection is just break up the order of operations with unnecessary code. You provision your memory space, and then you literally go increment some dead end variable a billion times. Now you come back, you copy your payload into memory, and then you go through and just calculate the Fibonacci sequence. You make it executable. And then before you make it executable, you literally just call 3 different functions that have nothing but a return back to the initial calling part, and then you run it. And by doing that, you threw all this spaghetti code and dead end code in there, but that can be enough to break up the behavioral detection that would have got you caught during execution. Also, don't be suspicious immediately. So I have had tests where all it took to get around the endpoint protection that I was trying to get up and running on was the fact that as soon as my unknown binary was executing, it was immediately calling out to some kind of web server. While an update function in a program might do similar behavior, for the most part, if it's an unknown binary and the first thing it does is it calls back to some kind of web server with encrypted data, that can be enough to get you caught. So if you can delay that, or if you can do some other actions before you try to do your C2 callback, that can be enough to get up and running. Another thing to be familiar with are the parent child process tree. So when you execute things, you are executing as a child of explorer.exe, say when you double click that file. Or if you run a command from CMD or PowerShell, what you're doing there is you're running as a child of that command interpreter. So a lot of security products are going to be looking for suspicious parent child processes. So there's no reason why Microsoft Word should be executing cmd.exe. There's no reason why Microsoft Edge should be executing PowerShell.exe. So these are things to think about when you're trying to basically build your story to the detection product as to what it takes to get around that. Another thing is try not to inject your stuff into a process that should never be talking to the internet. Notepad should never be calling back to a web server. Notepad should never be treated like a web browser. So a lot of times what we try to do, especially if we're going to be injecting into processes, is we try to inject into things that would be considered applications that should be talking to the internet, stuff like web browsers, chat clients, that kind of thing. Another thing is look at the memory protections. When you make that buffer, there are 3 different permissions that get applied to it. These would be the read, write, and execute, or the RWX. Rarely ever do legitimate programs nowadays set that memory as read, write, and execute. They typically make it either read, write, or read, execute, but not all 3. So now that we've kind of talked through that, we'll talk through some of our most common execution methods. These are basically just the file types and the applications that we have used to get up and running. So, of course, first and foremost is the portable executable, or the EXE. There's so many different ways that Windows takes advantage of this file format. So this is something that is pretty versatile and something that we still continue to use. And because of the way you can rename it, and depending on the location on file, that kind of thing, you can blend in with other legitimate processes. The only problem is that file type, especially as an initial access vector, is highly scrutinized. Even my grandma knows that you don't run executables that you downloaded from the internet. So you're going to have a really good social engineering pretext to get that up and running sometimes. and it can lead to detection just from the file type alone. So, because it came from the internet, because it's unknown, this can just be outright blocked. Another thing defenders can do is they can just block unknown binaries from running using application allow listing. When you're up against that, there are ways around it, but it does significantly raise the bar for getting up and running. But, when it's done right, it is one of the most common file types that we execute. So here's some of the different ways that we do execute it. Of course, you can just run it straight with cmd.exe or PowerShell, whatever command interpreter you've got. Another big one is explorer.exe. Now, this may sound obvious, but if you use explorer.exe with the /separate flag, what this does is it actually executes a new process of explorer.exe, the desktop environment that you have, and it'll run your payload as a child of that. But after about 30 seconds, 60 seconds, something like that, the secondary explorer.exe dies. So now your process will continue to run, but it doesn't have any kind of suspicious links back to an executing process. So that's a good way to kind of get up and running in memory without actually having any kind of long-standing suspicious parent-child process association. I kind of talked on this a little bit earlier with the MSI installer files. You can execute commands before and after your supposed installation portion. But another thing is if two certain registry keys are set, the always install elevated, you can actually execute as system from a low privilege user. A lot of system administrators, when we see this in an environment, they've done this because they have applications that have to update real frequently, and they want it to be able to be installed or updated. You'll also see this on developer machines, but it's not something we see nearly as much as we used to, but it is something to be aware of. Another thing is just creating a shortcut file. So say you want to run something that's already on disk, or you drop the shortcut along with the file, you can actually hide the execution of what you're trying to execute just by using the shortcut, and where it's doing a lot of wonky stuff in the background to the end user, all they did was double click something that looked like a PDF or something they expected to run. And then finally is service binaries. So these are a special kind of portable executable, but basically these are controlled by the service control app in Windows. If you have write access to a service binary directory and you can replace that service binary, you can actually gain persistence and privilege escalation all in one shot by having a service binary that can live on disk and be executed. So another very, very common tool that we use is MS Build. So this is a .NET compiler. It's associated with Visual Studio, along with being able to build out .NET applications from the command line. What's cool about this and the way we abuse it is you can do inline task files where you can actually put just stock C# as long as it's in a certain format in the XML with a certain kind of wrapper. You can actually just run stock C# code straight from MS Build. The biggest thing about this is, especially if we're in an application allow listing environment, this is very often a bypass for that because it's signed by Microsoft. In a lot of default application allow list configurations, or just in most environments, they're going to allow anything signed by Microsoft to run because of all the nature of all the applications that have to run with Windows. So another cool thing is getting your payload into the environment can be a little easier sometimes because it can bypass the static detections, since really XML is nothing but text. So another cool trick you can do with MS Build is you can actually change the .xml file extension from XML to CSPROJ or C# project file. If this file is sitting right next to the MS Build binary, it'll actually automatically ingest your inline task file and execute that code right off the bat. So one thing that we like to do is we'll copy MS Build out of its home directory, or we'll drop a modified copy that we have. We'll put the CSPROJ right next to it, and then we'll throw a shortcut file that calls our modified or moved MS Build file in the startup directory so that it will execute our payload every time the user restarts their computer. The good thing about the Windows logs files on this is that it actually will only show up as being executed with no arguments. So if it looks like something that should be running, it'll actually should at least go fly under the radar a little bit. And because it's C# code, you have full Windows API access. You can also separate out the C# code, especially if it's getting signatured, throw it on a WebDAV share, and your inline task file does nothing but reference that C# code out there on the WebDAV share. Another one is the install util. This is the .NET install and uninstall utility. This is also included with Windows 10 by default. Also an application allow listing bypass since it's signed by Microsoft. The only thing here is you have to compile the code into either a DLL or an executable, and it has to be dropped to disk. It can't be ran remotely, at least in my testing. I tried to figure that out, but I never was able to get it up and running very well using that method. The other thing about install util is it's only expected to run for a few seconds and then be done, right? So if install util has been sitting there running for 2 weeks in an environment, that very obviously can give away your malware. So it's something that you have to be aware of. Also, install util is not necessarily something that talks to the internet very often, so it is something that could possibly be an indicator of compromise. The only thing is, we still use this very frequently. We in social engineering, we'll set up like an ISO with the DLL, the install util DLL that we've compiled, and we'll make a shortcut file so that it looks like it's an installer for like Zoom or VPN software. And then what we'll do is we'll embed our DLL in there. We'll actually have a command to execute our DLL in the link file, and then throw in the real installation command there too, so that it looks like this was something that was supposed to happen. Finally, one of the most common things we use nowadays are proxy DLLs. Basically, this is a legitimate function from Microsoft where you can basically shim in code in between the application that's loading it and the legitimate DLL on disk. So, for example, C Windows System 32 version.dll gets loaded into almost every process out there. You can perform a DLL side loading or hijacking attack by putting something named version.dll. You export all the same function names that the real version.dll would export. And every time the application tries to call that function, it ends up running your code along with what it expected from the real version.dll. And because it's set up in a proxy DLL fashion, it'll actually send that call over to the legitimate DLL. So the application will continue to run without crashing, but you also are now loaded into a process that's expected to run. So I wanted to call out the Spartacus proxy DLL generator. It's actually Spartacus, not Spartan. I need to fix that. But that is a way to quickly generate a proxy DLL to play with. So one of the big things that we like to use with this is drop it beside a legitimate executable. So this would be something like applications that get installed to the user's app data folder, or say you have write access to a service binary. And because of the DLL hijacking attack and the way it works, it's going to grab your DLL before it goes and gets the real legitimate one. But now, let's say you did that with a service binary, you've also escalated privileges because now you're running within that service binary's process space. The other good thing is you can actually break the attack chain, because if you use something like a dropper to drop this proxy DLL to disk, you can actually you can say it gets dropped on Tuesday, the user shuts their computer down on Wednesday morning when they log in, now your C2 will be calling back. And because of that, you've actually broken the attack chain and made it a little more difficult to track down or at least spot right out of the gate. So in conclusion, I wanted to run through real quick just a couple of training options here, a couple of free blogs to check out. The 0x Pat blog, he has a lot of code samples there talking about sandbox evasion, and he goes into a lot of detail on why this works. So definitely check that out if you're looking for sandbox evasion code samples. Another one is the Cocomelon C blog. Basically, this mad lad basically will take any kind of code execution or sandbox evasion, and he will create it in C or C++, just so he can show you why this works. But there are a ton of entries with a lot of different code loading techniques already spelled out for you. So there are some paid training options. Sector 7, they have a ton of awesome malware development courses, and they're broken up really well with video examples for each, along with code samples. There's also the MalDev Academy or Malware Development Academy. That's a one-time cost for lifetime access, I believe, but definitely worth its weight in gold. Of course, I'd be remiss if I didn't mention that we have an intrusion ops course where it's red teaming from top to bottom, and one part of that course is something where we do actually take code, modify it, and get it up and running. The White Knight Labs guys have an offensive development course. If you can manage to catch that at one of the cons around here, it's awesome course. And then finally, the 0 Point Security Red Teams Ops course 1 and 2. Both of those have a little bit of malware, it's a little bit of malware development in the first one, but in the second one, that's the main focus of the course. Definitely worth checking out. Also included some resources, some GitHub repos to check out along the way. One thing we do take advantage of is the Ballast Kit, Shellcode Pack Pro, and Macro Pack Pro. A lot of really awesome evasion techniques built into this, and definitely worth checking out if your team needs something just to get up and running. So takeaways real quick, malware development is a field all of its own. I definitely wasn't going to teach you the ins and outs of it in an hour. This is very much a 101. I could only barely touch on a lot of the topics, but I wanted to kind of give a roadmap that would help people who want to learn more about this, kind of give you a jumping off point so that you have the concepts and some of the key terminology to go look into yourself. A lot of self-study and research is going to be necessary to use these techniques and to understand why they're not working when they don't. But understanding the method can help you understand why your EDR is breaking down at this point, because you can see exactly why these things were getting around it in the first place. So once you figure that out, it's a little easier to figure out what you can do to get your security products detecting these things. All right. And with that, I'll say good luck. Have fun.